Thank you very much, Julia. Also, Jens, for the invitation. It's a pleasure to participate in this Algebra Colloquium in Antwerp. So today I will try to show the importance of internal categorical structures in universal algebra, make a link essentially with torsion theories and the notion of semi-localizations in this context. So in order to explain these concepts, I would like first to compare the abelian classical context with the so-called semi-abelian context, would be the main environment we shall be working in. Then I shall explain how internal groupoids appear in this context, a few examples of torsion theories in the context of internal groupoids, and in the last part I will mention semi-localizations, which seem to be quite a suitable replacement for the notion of localization in this semi-abelian context. So first of all, let me begin by recalling what probably is the shortest definition of abelian category. So it goes back to the work of Buxbaum, who was a student of Eilenberg. We all know how important abelian categories are in homological algebra. And a very short way of defining an abelian category is the following. So one asks the category C to have a zero object that I shall denote by 0, binary products for each pair of objects A and B in C, and any map should factor as a normal epimorphism followed by a normal mono. So it's a very simple and intuitive definition of abelian category. And let me just recall that by a normal mono, I simply mean the kernel of some arrow in the category. So there is in C an arrow, say F, such that K occurs in a pullback of this type. So where 0 is the zero object of the category. Of course, in the category of groups, not necessarily abelian, normal monomorphism is the same thing as the inclusion of a normal subgroup up to isomorphism. So in the category of abelian groups, we all know that any monomorphism is normal. And the dual notion of normal epi somehow behaves more similarly in groups and abelian groups, in the sense that the definition is perfectly dual. You will say that Q is a normal epi if it occurs in a push-out of this form, where here again you have the zero object of the category. And you see here, both in groups and abelian groups, the notion of normal epi is simply the notion of surjective homomorphism. So there is no distinction as in the case of kernels, that is, of normal monos. So the typical example of abelian groups, as we all know, is the category of abelian groups. It has zero object, it has binary products, and any map factors as a surjective homomorphism followed by an inclusion as a normal subgroup in the codomain of the arrow. So f of x is simply the direct image of the homomorphism f. What about the category of groups, not necessarily abelian? Well, it is certainly not abelian, even though it has a zero object and direct products exist. The problem comes from the factorization, in the sense that any morphism in group has a factorization as a surjective homomorphism followed by an injective homomorphism, but this injective part is not a normal subgroup, it's just a subgroup. So this slight difference actually is quite interesting, and in somehow it explains why it took so long to find a suitable environment to treat the category of groups categorically in a similar way to the way that the notion of abelian groups the notion of abelian category allows one to consider the exactness properties of R modules and abelian groups. Same problem with the category of rings. Again, it is not abelian because in the direct image factorization, the inclusion of the image is not an ideal. So that's an abstraction from being abelian of the category of rings or commutative rings. So the question at the beginning, long time ago, I mean 1950, was the following: is there a simple list of axioms to develop a unified treatment of the category of groups, rings, and the algebras, for instance? It goes back to the paper by Saunders MacLean, Duality for Groups, where he proposed the first definition of what would have become later on, a few years later, the notion of abelian category. So in some sense, one wanted to find the fourth proportional in this proportion. The category of abelian groups is to the notion of abelian category in the same relationship as the category of groups is to what? So one wanted to find a suitable categorical context to treat groups. And a good test to verify if the proposed definition was suitable would have been, already in the words of MacLean, to check if the Noether's isomorphism theorems from group theory were true. And there was a goal of developing non-abelian homological algebra, radical theory, commutators, as one usually does in the category of groups. So as I said, after this famous paper by MacLean, Duality for Groups, there is the thesis of Buxbaum, where the notion of abelian category was introduced, and the famous paper by Grothendieck, Sur quelques points d'algèbre homologique, where the notion of abelian category became classical and unavoidable in some sense. But there were almost at the same time some attempts to introduce non-abelian contexts from the point of view of category theory. Certainly, one should mention, among many others, Kurosh-Amitsur for the theory of radicals, Higgins, who introduced the notion of variety of omega groups, Fröhlich, who was trying to do non-abelian homological algebra in this context, Gerstenhaber, Wheeler, and probably many others. Certainly, actually, many others. Now, only in 2002, there was a proposal of a solution to MacLean problem that somehow convinced category theories that it was a sufficiently powerful and simple list of axioms that would have allowed one to capture some crucial properties the category of groups and the algebras have in common, for instance. So they introduced what they called semi-abelian category, which will be the main context we shall be working in today. So again, one requires the zero object, binary sums, and a crucial notion in the definition of semi-abelian category is proto-modularity that was introduced in 1990 by Dominique Bourg. And it is the following property: whenever you have a commutative diagram of this type, where f and f prime are split epimorphism, and k is the kernel of f, and k prime is the kernel of f prime, if u and w are isomorphisms, then you can conclude that v is an isomorphism as well. So it is the split Schorfheim lemma, but it is important to observe that here we do not ask that f is the co-kernel of k and f prime is the co-kernel of k prime. We only ask that k is the kernel of f and k prime the kernel of f prime. And it follows in a proto-modular category that then f is the co-kernel of k and f prime is the co-kernel of k prime. And then the other important ingredient besides proto-modularity, the notion of bar exactness. So when I ask that in the category C, every arrow f has a regular epi monofactorization. By a regular epi, I mean simply the co-equalizer of two arrows in the category. one has the factorizations are pullback stable, and that any equivalence relation R is effective. So that if R is a relation on A, then you can always find an F such that this square is a pullback. So the category of groups is the prototype of semi-abelian category. As we observed already, we have this factorization as a regular epi followed by a monomorphism, which is not necessarily normal, but still is a monomorphism. These factorizations are pullback stable simply because surjective homomorphisms are pullback stable in sets, and they are also so in the category of groups. The split-Shor-5 lemma is known to hold in groups, so it is a proto-modular category. And one can check that if you have an internal equivalence relation in the category of groups, that is an equivalence relation which is also a subgroup of the product, if it is a relation on X, say of X times X, then when you take the co-equalizer, it is the kernel pair of its co-equalizer. So this equivalence relation is again effective. And essentially for the same reason, rings, associative algebras, Lie algebras, general varieties of omega groups are all examples of semi-abelian categories. If you take internal groups in compact Hausdorff spaces, so compact groups, they form also a semi-abelian category, as do pro-finite groups. In general, if you have an exact category in the sense of bar, and you take internal groups in C, you will always get an exact proto-modular category. Then you have to require that this category has co-products to say it's semi-abelian. Of course, any abelian category is in particular a semi-abelian category that is expected. And actually, there is a nice relationship between abelian and semi-abelian in the sense that a category C is abelian if and only if both C and its dual category C-op are semi-abelian categories. So I will speak now of the example of cross modules. So cross modules were introduced by Whitehead a long time ago, and the objects of this category are a group homomorphisms alpha from A to B with an action of B on A, such that alpha applied to B that acts on A is B times alpha of A times B minus 1. And on the other hand, the Pfeiffer identity holds, which means that if I take an element A, apply alpha, and then I look at the action of alpha of A on any element A1 in A, then I get A1, A minus 1. The morphisms in this category are also quite natural. They are commutative squares, more precisely pairs of group of morphisms F0, F1, making this square commute and preserve the action. So if I have A and B in the group A and the group B, I can either first apply F1 on A and F0 on B and make F0 of B act on F1 of A, or apply F1 to the result of B that acts on A. And these two elements should be the same. So this category of cross modules is again semi-abelian. It is actually equivalent to the category of internal groupoids in the category of groups. So this result was somehow folklore for a while. It was proved by Brown and Spencer, published by Brown and Spencer first, but apparently in the school of Verdier it was already known. And we shall see actually that it is the fact that cross modules is a semi-abelian category is a special case of much more general result. So Dominic Bourne and George Janelidze tried to characterize those varieties of universal algebras which are semi-abelian. So by a variety of universal algebra, I mean a class of algebras of the same type, that are determined by finitary operations and some identities. These kind of varieties are really the varieties studied in universal algebra. And if one looks at the properties that are needed on free algebras in order to ensure that the split short-five lemma holds in the variety, one finds out the following characterization. So you need a unique constant in order to make your variety pointed. And then you need n binary terms, alpha 1 of xy, alpha n of xy, and an n plus 1 array term beta, so a term with n plus 1 variables, such that on the one hand, alpha I of x is 0, and on the other hand, if you apply beta to alpha 1 of xy, alpha n of xy, y, then you get x. So the point is that one should think of these alpha i's as generalized subtractions and beta as addition. As we see in the next slide, whenever you have a variety of universal algebras containing the terms and the axioms of a group, then the variety is semi-abelian. It suffices to take a unique constant 0 as binary term alpha 1 of xy equals x minus y, and as binary term beta of xy, the addition x plus y. And of course, if you do alpha 1 of xx, you get 0 as required. And if you mix beta with the unique alpha I you have, you get x minus y plus y, namely x. So this is simply the proof that the axioms of a group guarantee that your variety is semi-abelian, provided the Born and Janowitz result is correct, which is the case. So it is interesting that this list of axioms, without any reference to split short-five lemma or homological motivation, so these axioms were introduced independently by Orsini long before the notion of semi-abelian category was introduced. In some sense, Orsini realized that by choosing varieties with these terms, one could develop a good part of the theory of commutators that one knows for groups in the context of general varieties of universal algebras. So he had a different name for these varieties, but it turns out that whereas Dominique Born introduced proto-modularity essentially to have suitable exactness properties to do homological algebra as one does in groups, Orsini had a different goal, which was the fact of developing commutator theory. And these two approaches gave the same list of axioms. So categorically, they correspond to the fact that the category you're working in is pointed, exact, and especially proto-modular. So it turned out recently that also cocommutative Hopf algebras, they form a semi-abelian category. So K is a field, and you probably all know what K by algebra is. So just to fix the notation, you have the multiplication, the unit, the co-multiplication, co-unit. You have the associativity, co-associativity axioms, and the unit and co-unit axioms. And moreover, we are interested in Hopf algebras, so we need also an antipode S, which is a linear map making this triangle commute. So to be commutative, your Hopf algebra also has to make this diagram commute, where big delta is the co-multiplication. And we use the Sweeter notation for delta of A. So this A1 tensor A2 is actually a sum, as usually in Hopf algebras. So in this context, what we proved with Joost, that I think is here, and I say hello to him, and Florence, was that for any field K, actually the category of cocommutative Hopf algebras on a field is semi-abelian. And the Proto-Modularity somehow was already known, because if you take internal groups in a category with finite limits, it is always proto-modular. But the difficult part was actually to prove that it is regular, and more specifically, or exact, and more specifically, the fact that regular epimorphisms are pullback stable. And for that, you really use the cocommutativity of the Hopf algebras. And this result in particular gives back an old result by Takeuchi that says that if you take cocommutative and commutative Hopf algebras, then you get an abelian category. And the way you can deduce the corollary from the theorem is quite simple. If you know that cocommutative Hopf algebras form an exact category, actually, then if you take abelian groups in an exact category, you always get an abelian category. And so what you need to know is that commutative and cocommutative Hopf algebras are the same as internal abelian groups in the category of cocommutative Hopf algebras. And the fact that this equality is explained by the fact that cocommutative Hopf algebra is abelian if and only if the diagonal, which is the co-multiplication, is a normal monomorphism. And this is easy to see that the image of the co-multiplication, delta of A, is a normal subalgebra of A tensor A, if and only if A is commutative. And so, if and only if your algebra, which was assumed to be only co-commutative, is also commutative. So, in full generality, if we start from a semi-abelian category, you can always take internal abelian objects in C. And this category is actually abelian. And what is interesting is that in a semi-abelian context, being abelian becomes really a property, in the sense that on any object A, you have at most one multiplication making it an internal abelian group. So by an abelian object, of course, we mean an arrow in the category making the suitable diagrams commute. And the point is that when NA exists for an object A in a semi-abelian category, then this multiplication is unique. So you cannot have two multiplications on the same objects. So being abelian becomes a property in semi-abelian category, actually in a more general categorical context, but we concentrate today on the semi-abelian context. And what is even better is that not only it is a full subcategory of C, the category of abelian objects in C, but it is reflective, and you have really an abelianization factor as you have in the category of groups. So you make the quotient of your A by a suitably defined normal subobject of A that can be defined using a certain co-limit construction. And of course, this adjunction extends the classical one between groups and abelian groups, but it is much more general because you have plenty of examples of semi-abelian categories which are not groups. So in this particular case, of course, the abelianization factor is simply the quotient of G by the derived subgroup of G. And so the subgroup generated by all the commutators of XY for X and Y in G. Now, how can we define the categorical commutator in a semi-abelian category? So first of all, one has to take two normal subobjects, say M and N, and then one considers the condition of having trivial commutator. So when this commutator is zero, when they commute. So we shall use this symbol mn equals 0 when you can find an arrow P from the product of m and n into A such that these two triangles commute. So what is this diagram? We have M, which is a subobject of A, N, which is a subobject of A. We assume them to be normal in this particular situation. And you have two canonical maps into the product, identity 0 and 0 identity. So this exists always when you are in a pointed category. Then you say that the commutator is 0 if there is an arrow P making these two triangles commute. So the case of groups will explain where this definition due to Hack come from. Assume first that there exists such a P making these two triangles commute, and consider the product m times n. Now, since this triangle commutes, P of m1 is equals to m. Since the right-hand triangle commutes, P of 1n is n. Then you use the fact that it is a morphism of groups, so you can write P of m1 times P of 1n equals to P of mn, and then you simply write mn as 1n times m1, and you use again the two commutativities to conclude that mn equals nn. So two normal subgroups of a group G commute in the sense of commutators if there is a group morphism P making these two triangles commute. One should also check, of course, the other way around, assuming that you have the classical commutator of n equals to 1, then this map that sends two elements m and n to their product is a group morphism provided this condition holds. So the condition of the commutator of m and n being trivial guarantees that the map P of mn equals m times n is not only a set theoretic map, but it is a group morphism. Now, the case of cocommutative Hopf algebras is similar because the product, the categorical product of two objects is here given by the tensor product. So if you have two maps in the categorical commutative Hopf algebras to morphisms f and g, then the morphism phi given by f tensor g composite with the commultiplication is the required factorization to this object, showing that the tensor is the categorical product. And then you can say that two Hopf subalgebras have trivial commutator if there is a morphism P making the same two triangles commute, where you have replaced now the product of groups with the tensor product. And one can see actually that this morphism P has to be the multiplication, and it is a morphism in the category of Hopf algebras if and only if xy equals yx. Or equivalently, if in Swedish notation x1, y1, s of x2, s of y2, where s is the antipode, equals epsilon of x times epsilon of y. So this is the commutator that you can define categorically through the product using the Hack commutator, and you can describe explicitly as the subalgebra generated by all the elements of the form x1, y1, s of x2, s of y2 for x in x and y in y. Now, the point is that this commutator, this Hopf subalgebra, satisfies what is usually required for the universal property of the commutator. So in a general semi-abelian category, if you have two subobjects x and y, we shall always assume that subobjects to be normal, but you can define more generally. Then the commutator of x and y is the smallest normal subobject of A, such that the images Q of X and Q of Y along the quotient commute. So this means the following diagrammatically. You start with two subobjects X and Y of A, and you are looking for the smallest normal subobject of A, such that when you go to the quotient A over C, then Q of X, the images, Q of Y, images that exist because you are in a semi-abelian category, factor through the categorical product of Qx times Qy. So it is the most economical construction needed to make the images of X and Y along Q in the Hopf sense. Now, another thing you can do in semi-abelian categories is really to use these exact sequences as we did here. We are constructing a short exact sequence as we are used to in abelian categories. You can do it also in a semi-abelian category. And actually, one of the good things of this context is that you can prove, as MacLean suggested, for the nether isomorphism theorems, snake lemma, 3x3 lemma, all the homological lemmas that are usually used in abelian context. You can also have a form of the Jordan-Hölder theorem, for instance, in any semi-abelian category. And the general idea then is the following. An abelian category can be seen, thanks to Tierney's theorem, as a bar exact category, which is moreover also additive. And in the proto-modular, I mean, in the semi-abelian case, so the non-additive version of this equation, so to say, is to replace additivity with a zero object and proto-modularity. So the split short-five lemma replaces the additivity. Of course, you lose some properties when you weaken your axioms, but you can treat many, many more examples that are not abelian. And so there are abstract notions. I'm not going to speak of all of them today because I want to concentrate on groupoids, but you have commutator that I already mentioned. You have so the notion of centered extension, centered series, the notion of internal action, and there's a notion of semi-direct product, which is categorical. You can develop a non-abelian cohomology. You have a notion of torsion theory, which I'll come back to that later on in the talk. So probably it's a good moment to stop to ask if there are questions.
Hello. Yes, I hope you can hear me well. My connection is very bad, but I have a question.
Yeah.
You have a lot of things that do transfer to the semi-abelian case, but is there an important thing that is lacking in the semi-abelian case opposed to the abelian case?
With respect to groups?
No, you say, for example, a lot of the abelian notions you can also generalize to semi-abelian, but what is there something important that's really lacking in this case?
Well, thank you for the question. There are a few things that are lacking, of course. It's difficult to say which is the most important. Let me think a moment. But the most striking one is that you lose self-duality. So the axioms are no longer self-dual. Very often in a abelian context, you can do one proof and then you already get the dual result for free. So this is no longer possible because of this asymmetry between normal mono and normal epi that I mentioned at the beginning. So that is technically a big difference. Another thing is that what we are going to actually see in a few minutes is that internal structures, so you lose something, but you also see things appearing, because after all, commutator theory essentially does not exist in the abelian context because everything commutes. So it's true that you lose, for instance, byproducts. You no longer have byproducts in the semi-abelian context, but on the other hand, you see new notions playing a role that you cannot really express in the abelian context because the context is too strong. So typical example is commutators. Well, other things that you really miss. I think, yes, the additivity and the byproducts is the big difference between semi-abelian and abelian, and the canonical factorization that you have from coproducts, from a binary coproduct to a binary product, is no longer an isomorphism. It is a regular epi, actually a normal epi. So it is a quotient. And in some sense, this distance between the co-product of two objects and its product is really what measures the difference between abelian and semi-abelian world, so to say.
Yeah. Okay. Thanks. That's really enlightening.
Thanks. Okay.
Yeah, then you go ahead.
Thanks.
I think there's a part of the question. Yeah.
Hi, I have a question.
Yes,
are the
please,
sub-objects still well behaved? Like, do you lose anything with the sub-objects?
I'm not sure. Sorry to understand fully your question. I'm sorry.
Like in abelian categories, your sub-object, all the sub-object, you have sub-object lattices, is what I'm trying to say.
Yes. Thank you a lot. Now I understand. Now I understand your question. Sorry.
Cool.
So one thing that you have in semi-abelian context about sub-objects is that they form a modular lattice. So this is something that is quite well known in the universal algebra context, in the sense that to develop commutator theory, one natural condition to consider is actually to ask that congruencies on each algebra form a modular lattice. And you have this nice property already for normal sub-objects in any semi-abelian category. So I think this is the most, the strongest property you get. If you ask distributivity of the lattice of sub-objects, then you get some examples like height semi-lattices, but their commutators become trivial in the sense that they coincide with the intersection of two sub-objects. So the most natural and important condition, I think, on sub-objects on normal sub-objects in a semi-abelian category is modularity.
Cool. Thank you.
I think there's still one question.
Yes.
Wendy, yeah.
Yes, thank you. Hi, Marino. Yes, I have a question about this nice proportional you put up at the very beginning. So abelian groups as a prototypical example of abelian categories, and now you're looking for something playing the same role with respect to groups. So, of course, in the abelian setting, looking in the other direction, abelian groups, the category of abelian groups plays a very special role. Also, if you're talking about additivity just a minute ago, for instance, in the sense that every abelian category is canonically enriched over the category of abelian groups, and there are other things one can say. I was wondering, is there a reason for taking groups in the semi-abelian case? Is there a hierarchy, or could I also have taken, for instance, rings as my prime example, and that the main question is we're trying to axiomatize the fundamental things in rings, or is there something more to groups?
Yes, thank you very much. I think this is a very important question in the sense that it is one of the reasons why it took probably 50 years before proposing a common framework for all these constructions that one would like to make in groups and in rings, for instance. So clearly, abelian groups have a better dominant position in abelian categories with respect to the project, with respect to groups in this project of non-abelian homological algebra and universal algebra. It is true that semi-abelian category is not the answer. I mean, I've been working in this field for a while, and it's clear that semi-abelian categories provide a very nice answer where many things you can do, But then there are some specific aspects which only hold if you add some axioms which are more directed towards groups or towards commutative rings or rings. So it is for this that it is quite amazing that, for instance, for the needs of non-abelian homological algebra and commutators, basically this notion of semi-abelian category seems to be very efficient. But if you want to do radical theory and if you want to go into representation theory, I mean, you might add some different axioms that are more efficient. So after finding a common core, I would say, of the properties one would need in order to do what we are used to do in the category of groups, rings, and the algebras, now a direction of research is actually towards finding axioms that make a difference between these directions. So to add some specific additional axioms to semi-abelian that will make it more similar to groups or more similar to commutative rings, for instance. So there are some specific notions that probably I will not have much time to speak today, but that seem to be more peculiar to some specific model. So.
Oh, okay, thank you very much.
Thank you.
May I?
Yes, please.
I'm curious. You've introduced these semi-abelian categories.
Yes.
I mean, it's well known that abelian categories have a derived category associated to them. Is there something you can do along these lines? There is maybe you told about at some point, I think, of non-abelian cohomology or something. Is there something one can do?
No, yes. So there is a lot one can do, but not really in direction of derived categories, in the sense that this world I'm speaking about is eminently non-additive. And so what you can do is to define homology and cohomology objects. There are some theorems of classification or central extensions via cohomology. For instance, Tim van der Linden did a lot of work in that direction. There is a possibility of establishing some Hopf formulas for homology, as you have in group homology, for instance. But the methods are different, essentially different from the ones in derived categories. So there is no something that corresponds to derived categories in the context of semi-abelian categories. Nevertheless, one can deal with homological and cohomological properties, essentially following some ideas that come from Fröhlich school and Gerstenhaber approach to homology and cohomology, and probably one would need a talk about this because it's a very wide subject at the moment.
Thanks.
Good. So I think I'm a bit late. Probably was too ambitious with the number of pages, but it's not important if we don't get really to the end of the talk. It's more important that we have the possibility of discussing. So the next thing I would like to speak is about internal groupoids in this algebraic context. So in an abelian category, any reflexive graph is equipped naturally with an internal groupoid structure. So this is something which is well known for many years, even before semi-abelian categories were introduced. Let me take the example of abelian groups. So this diagram in the middle represents an internal groupoid in C, and the pullback is given by pairs of arrows. So one should think of elements in X1 as arrows, X0 as objects, and elements in X1 times X1 over X0 as pairs of arrows whose domain of the first component equals the domain of the second component. So the codomain of the first equals the domain of the second. So this X1 times X1 over X0 in abelian groups is given by arrows of the form X y, f from x to y, and g from y to z. So these are composable arrows. So if you have a reflexive graph without having anything else in abelian groups, then you define a multiplication M of f and g by simply putting g minus identity on y plus f. So these are now elements in x1, and you have in x1 an addition and a subtraction. So you can define a new map, M of fg, that associates with two composable arrows in this object of composable arrows, a new arrow, which is g minus identity on y plus f. And this gives you a groupoid structure, actually. So you have a functor in the case of abelian groups from the category of internal groupoids in AB into reflexive graphs in abelian groups, which is a category isomorphism. This was called a long time ago the Louvain condition, because he pointed out this property that actually additive categories already have. And this is not the case if you go to groups. So a reflexive graph, so a diagram like this, where if you first apply E and then D, you get the identity on x0, and same thing E and C, you get the identity on x0. So such a reflexive graph is a groupoid if and only if a commutator condition holds, namely the commutator of the kernel of D and of the kernel of C is trivial. So among reflexive graphs, those underlying a groupoid structure are characterized by this commutator condition. So you need more than a reflexive graph to get a groupoid, but not much more. You need some commutativity conditions on the kernels of the domain and the codomain of your potential groupoid. And so this, of course, makes many of us think of the one-cut groups of Jean-Louis Laudet. And it turns out actually that you have the category of internal groupoids in groups, the category of reflexive graphs in groups. You have a forgetful functor, and you have a left adjoint to it. For any reflexive graph, say x1, x0, domain, codomain, this gives the identity arrow. You keep the same object, actually group of objects, and you make a quotient. You make the quotient of x1 by the commutator of the kernel of D and the kernel of C. So you get a new reflexive graph where D bar and C bar, so the induced domain and codomain arrows, actually have now trivial commutator. And so here you have a groupoid structure. So you are making any reflexive graph an internal groupoid universal. So the commutator of Hopf subalgebras that we mentioned before, using the product, which is the tensor product in the cocommutative Hopf algebras, allows us to describe the reflexive graphs, which are underlying a group of structures, essentially in the same way. So if you take a reflexive graph in cocommutative Hopf algebras, so a reflexive graph is precisely a diagram of this type satisfying these identities, then it will have a groupoid structure if and only if the commutator of the categorical kernels of D and C is trivial, which is equivalent to asking that the product of the elements xy and yx are equal for any x in the kernel of D and for any y in the kernel of C, where the kernel in cocommutative Hopf algebras can be computed as the x in x1, such that x1 tensor D of x2 equals x tensor 1. And this characterization of groupoids inside cocommutative Hopf algebras and inside groups remains true essentially in any semi-abelian category. And actually, you need less than semi-abelian. It is what usually called the multi-category. It is a nice context that is more suitable to do commutators than to do homological algebra. And basically, one can simply forget about this massive property. It's a property that is true, say, in in any semi-abelian category. It says that you have when you have a reflexive relation in C, then it is automatically an equivalence relation. So it has a symmetry and it has a transitivity. So you start with a reflexive relation, then it is automatically an equivalence relation. And one can also ask equivalently that the category C has the property that any reflexive relation in C is symmetric. So just to convince you that this makes sense, let's prove that the category of groups is a Maltsev category. So what is an internal reflexive relation on a group A, say? It is a reflexive relation on the set A that is also a subgroup of A times A. So if you take xy in this relation R, since R is a subgroup of A times A, then the inverse of this element, xy minus 1, belongs to R, because it is a subgroup. So the inverse of xy is precisely the pair of elements x minus 1 and y minus 1. Now, your relation here, R is reflexive. So from the fact that xy is in R, you deduce that xx is in R. We have already observed that x minus 1, y minus 1 is in R, and yy is in R because R is reflexive. But since it is a subgroup of A times A, I can multiply xxx with x minus 1, y minus 1 with yy. And I get x minus 1, y, and in the second component, I have x, y minus 1, y. And after simplification, you see that yx is in R. So any reflexive relation in groups is automatically symmetric and also transitive, by the way. And this property defining Maltsev categories was actually comes from universal algebra, where Maltsev varieties are usually called two permutable varieties, because this property that any reflexive relation is an equivalence relation internally is equivalent to the fact that the composition of two congruences, so of two equivalence relations in the variety, permute, so that R composite with S equals S composite with R, where R composite S is given by the AB in A times A, such that there is a C with AC in S and CB in R. So this is just for the terminology. So it turns out that when C is an exact Maltsev category, then the category of internal groupoids in C is again exact Maltsev. So this is a very algebraic property. So it keeps the same good properties of the base category C. And the crucial property for this theorem is the regularity of groupoid C. So the fact of describing the regular epimorphism in groupoid C as those morphisms of reflexive graphs from X to Y, such that both F0 and F1 are regular epis. Let me just point out that this is not true in sets. So if you take the category of ordinary groupoids, it is not even regular. Regular epimorphisms are not pullback stable. So when you internalize the notion of groupoid inside an algebraic category, which is, for instance, semi-abelian or more generally exact Maltsev, then you get, again, a category that has the same good properties as the category you started from. And actually, I mentioned congruent modularity before about the lattice of normal subobjects, but in universal algebra, you do not require, in general, that you have a zero object. And you say that a variety is congruent modular when the lattice of congruences on any algebra is modular. So it satisfies this equality whenever T is less or equal than R. And with Irka-Bozitsky, we observed that for a modular variety, the fact of being a Maltsev variety is equivalent to the fact that groupoids form a subvariety of RGV. So by a subvariety, I mean a full subcategory that is reflective, and it is closed under quotients and subalgebras. Usually in universal algebra, one asks the stability under products, homomorphic images, homomorphic images and subalgebras. But it is equivalent to ask that these groupoids are actually very well behaved with respect to reflexive graphs. And we saw already that to get universally a groupoid out of a reflexive graph, you simply have to make a quotient. So it's a particularly nice situation. And it is characteristic of these Maltsev varieties. And when we go back to semi-abelian, then you get the C is semi-abelian if and only if the category of internal groupoids is semi-abelian. So it really keeps the same good properties as the category C you started from. Now, this category, if you take any semi-abelian category, you can always how do you say, embed it into the category of internal groupoids via the discrete functor. And this has a left adjoint, which is the connected component functor. So if you start from a groupoid, say x1, x0, then you simply take the co-equalizer of domain and codomain, and you take the discrete internal groupoid, which is an equivalence relation on this object, and you have a canonical map towards this groupoid, which is discrete, and this is the unit of this adjunction. So what I wanted to say here is that we have a nice connected component functors, which exists, of course, also if the category C is not semi-abelian. But what you do have in the semi-abelian case, let me just mention this, is that pi 0 is proto-additive. So it preserves all split short exact sequences. So a proto-additive functor is somehow what replaces additive functors in this semi-abelian context. Of course, if the C and D are two abelian categories, then to be proto-additive, namely to preserve split short exact sequences, is the same as being an additive functor. But when you go to semi-abelian, various equivalent ways of expressing additivity of a functor are no longer equivalent. So you have to choose one. And we believe that, I believe that this notion of proto-additive functor is particularly useful in the semi-abelian context. So whenever you have a split short exact sequence, then you apply your functor, you get again a split short exact sequence. Now, any groupoid in C determines actually a short exact sequence in the category of internal groupoid. So we start from our internal groupoid X, we take this unit of the adjunction, so the pi 0, and then you take the kernels horizontally of the two maps, and we get here another groupoid. Now this left-hand groupoid is actually a connected groupoid, and this is a canonical short exact sequence that you can associate with any internal groupoid in C. And so, more precisely, this gamma x of 0, if you look at what it is, for instance, in sets, but in pointed sets because you need 0, but it is the full subgroupoid or the connected component of 0. And what does it mean for a groupoid to be connected? I remind you, a groupoid X is connected when the canonical arrow from x1 into the product x0 times x0 is a regular AP. So the category of connected groupoids is equivalent actually to the category of central extensions. Recall that in groups, central extension is simply a surjective group of homomorphisms with the property that the kernel is contained in the center of its domain. So the same now can be expressed in our semi-abelian context. So we say that F is a central extension if its kernel has trivial commutator with the largest subobject on A, which is A itself. So you have a normalization functor that will take a connected groupoid to, so you start from this diagram, you take the kernel of the domain, you compose with the codomain, and this is a central extension. And it is actually a category equivalence. Now, this pair, connected groupoids and C, is an example of a non-abelian torsion theory in the category of internal groupoids. So this is a good point where to stop. I hope I don't have to stop quickly, but how much time do I have? Do I still have 5 minutes?
Yeah, for sure. I mean, having some questions in the middle, we still have time, definitely.
Okay, so I go on and recall you some properties of these torsion theories. So the classical notion of torsion theory in any abelian category was given by Dixon. So you have a pair of full subcategories which will always be replete, say tau and x, such that for any object C, you have T of C in the torsion part and F of C in the torsion-free subcategory. Moreover, the only morphism from an object in the torsion subcategory to an object in the torsion-free subcategory is the zero morphism. And usually one calls tau the torsion subcategory of C and X the torsion-free subcategory of C. So the classical example you certainly know is the torsion abelian groups and torsion-free abelian groups in the category of abelian groups. And this canonical short exact sequence that you associate with any C is actually the quotient of C by the elements in C, which have finite order. So there exists n such that nc is 0. So this short exact sequence that you find in the torsion theory gives you the reflection to the subcategory of torsion-free abelian groups. So sorry, I have to be a bit fast. So this reflector F is semi-left exact in the sense of Cassidy-Hebert-Kelly. So it is not really important what semi-left exact means. What is important is that it preserves some pullbacks, not all of them, which would make it a localization. But a certain type of pullbacks of this form, where eta is the unit of the adjunction and u of x is a morphism that lies in the torsion-free subcategory of C. So to conclude, since there is not much time, Wolfgang Rump characterized the exactness properties that characterize torsion-free subcategories of an abelian category. So if you take C that is abelian, imagine that you have an X for which you can find a tau with the property that tau X is a torsion theory. Then you can prove that X is additive, that any morphism F has a factorization Q, G, K, where Q is a normal epi, K is a normal mono, and G is a bimorphism, namely a morphism which is at the same time a monomorphism and an epimorphism, but not necessarily an isomorphism. So this is what he calls almost abelian categories in this additive context. So it is additive with this factorization, and he asks that normal epimorphisms are pullback stable. He has some examples which are all additive, of course, any abelian category. It's a generalization of abelian categories in another direction, but that remains additive. So you have abelian topological groups, abelian Hausdorff groups, Banach spaces, locally compact abelian groups. So in the non-additive case, there has been many results in the last years to study torsion theories therein. And there are several new examples that have been discovered in the category of compact groups, of groupoids in groups, in Hopf algebras, in pre-ordered groups more recently. So the question that Steve Lack and I studied a few years ago was to find a characterization of the torsion-free subcategories of a semi-abelian categories, very much in the same style as Rump did for abelian categories. And the definition of torsion theory in a semi-abelian category is exactly the same as the one by Dixon that I recalled before. So let me just conclude with some examples. Of course, you have groups which are torsion-free in the category of groups. You have groups inside the category of groupoids in groups that you can also see as cross modules. You can also take internal equivalence relations in groups inside groupoids in groups. This is another example of torsion theory. Here, the canonical short exact sequence, starting from internal groupoid X is obtained by taking the regular epi-monofactorization of D and C. And then you take the kernel. The kernel here is an internal groupoid with 0 as object of object. So it means it's an internal group. Actually, it is an abelian group. It's an internal abelian group. Yes, I'm afraid I have just to give you the result. Yes, and the result basically, sorry for skipping all these details, but I thought I was faster. So we need a new definition of proto-modularity, a characterizing property of proto-modularity in order to treat torsion-free subcategories of semi-abelian categories. And it turns out actually that the category of internal groupoids in C is exactly the exact completion of the category of internal equivalence relations in C. So inside groupoids, you have those groupoids for which domain and codomain are jointly monic. These are internal equivalence relations. They form a category which is not exact in the sense of bar, but it is only regular. If you consider the exact completion of this category, then you find out that this is precisely given by the category of groupoids. And to conclude, because really I'm out of time, probably I can just mention this, that internal groupoids are used, so in commutator theory in universal algebra, they appear quite naturally in homological and homotopical algebra as cross modules or cross squares. Cross squares correspond to double groupoids in the category of groups. All this can be done in the context of semi-abelian category. The category of internal groupoids in C is a non-abelian torsion theory. So, I mean, gives rise to several examples of non-abelian torsion theories. And it is also a solution of this universal exactness problem that we solved with Steve Lang. And finally, internal groupoids also in algebra have a central role in the so-called fundamental theorem of categorical Galois theory that allows one to classify coverings of suitable adjunctions in terms of actions over the suitable Galois groupoid. So this part I didn't have to say much, but it is more, so I hope that at least this talk gives some ideas of the kind of constructions one can do in the context of semi-abelian categories with internal groupoids. At the same time, you can do homology, you can do commutators, you can treat torsion theories, and in the next occasion one could speak of this categorical Galois theory. So thank you very much for your attention and patience.